this presentation, we're going to take a look at some people who freeze to please. They don't mind cold temperatures. They actually subject themselves to freezers and throw them in and then spray this fine mist to see what happens to airplanes when they collect ice. So this section is all about aircraft icing. And yes, as you can see from this opening photo here, we actually have a case where NASA was investigating icing, and they took this great big Chinook helicopter, had a twin otter trailing it, and then on purpose took a hose with temperatures below freezing outside and sprayed the airplane with water. Well, the results looked something like this. You can see all sorts of ice covering this twin otter, all along the windshield here, and then really gets interesting later on when we start to look at the wing back here. Now, we'll zoom in on that wing later on and take a look at it. But what you see is something kind of like these pictures here. Now, if I remember correctly, these technically were taken from the vertical stabilizer and then flipped during our editing process just to, see the texture a little bit better. So this really isn't quite what you'll see on the wing in terms of structure, but you still see a lot of ice after this testing. So to get icing, what are the two things that are most important? Well, you don't really want to get it to begin with, but there's two conditions that we need in order to get icing, and those two conditions are as follows. We need some sort of visible moisture. So what that means is if you go flying through a cloud, or let's say you fly through rain, you could get icing if the second condition is met. And that second condition is that the temperatures must be below zero. So those are the two main ingredients for icing: visible moisture, and then from there, temperatures below 0 degrees Celsius. If you remember those two parts of that little equation and eliminate one of them, you are most likely not going to get icing. So keep that in mind. But let's start to move into some of the more theoretical aspects of icing. First of all, why does it form? You would think that at temperatures below 0 degrees Celsius, that if there's any sort of water in the atmosphere, that it would freeze and become something like snow. Well, not always. In order for this to happen, for ice crystals to start to form, it's really helpful to have little things floating around called condensation nuclei. If you can get water droplets to attach to that, and it could be something most commonly in clouds below zero, a small ice crystal, all the rest of the water droplets will start to happily condense onto those particular little ice crystals. Technically, it would be more almost like sublimation. Now, that said, water in the absence, you can see right here, supercooled water droplets. So this is water droplets existing below 0 degrees Celsius up to temperatures of minus 40 degrees Celsius. Supercooled water droplets tend to favor locations with decreased condensation nuclei levels, and part two of this equation is vertical currents. Okay, so if I'm a water droplet and I'm at a temperature of, let's say, about minus 8 degrees, it is possible for me to exist in that liquid form. If there isn't a whole lot of condensation nuclei around, or other ice crystals, which are a type of condensation nuclei, then I can just exist in that liquid state until the biggest condensation nuclei collector in the world comes passing through. And that happens to be an airplane. An airplane with a skin temperature of 0 degrees or less, aka, in this case, the NASA testing, the twin otter. All right, so now this twin otter rip-roars through all of that wet, cold, supercooled water. It's below 0 degrees Celsius. Guess what happens to all that water? It instantly freezes. And this airplane begins to become an ice cube. All right. Now, when it comes to icing, we've identified three major types. Now that said, it tends to be that the three major types will end up usually being mixed ice, because mixed ice is a combination of rime ice and clear ice right here. Now, what I want to do for a few moments is I'll go to the whiteboard, but I'll give you a little bit of background just before we go there. When we look at rime ice, what we are typically looking at is smaller sized droplets. Later on, we'll talk about how droplet size changes the rate at which an aircraft will collect the ice. So, rime ice tends to be smaller droplets. Clear ice tends to be larger droplets. There's also certain cloud types typically associated with these. Now, of course, as I mentioned, most commonly ice will be mixed ice, so it will be a combination of these two. But let's go over to the whiteboard for just a few moments, and let's look at how it is that these two types of ice end up getting differentiated. All right, let's do that. So what we'll start out with is we'll start out with a very simple airfoil. So here we go. There's that simple airfoil there. And we are going to imagine that we have all sorts of droplets of water, and those are all heading towards the wing's leading edge. What we will do is we will actually now, this zone right in here, we want to pay particular attention to this zone. So I am going to zoom in on this particular zone here, and we will draw the leading edge significantly larger so that we can take a little bit of a look at what is happening. So right at the leading edge there. With rime ice, typically we can have various droplet sizes. Typically, with rime ice, it's going to be smaller droplets. And what will happen as these smaller droplets all rush towards the leading edge of the wing, because they're small, as soon as they touch, remember this could be at like say minus 10 degrees Celsius, this airplane skin, as soon as these droplets touch the surface, they're going to freeze. So what will happen is each one of these droplets adds itself to the wing. You're going to end up with, as you can see, little spaces in between each one of these droplets, little air pockets. So when it comes to rime ice, what we have is instantaneously freezing, typically small droplets, leaving little air pockets in between. So this type of ice, what it will do is it will usually form kind of like I'm showing you here, like a spearhead. So it will kind of straight out towards the incoming airflow. Other nice things about this is that, well, it tends to be a slightly lighter type of ice. Now, it's still not good because look at what we're doing to the shape of the airfoil. We're significantly changing the shape of the airfoil. So we're becoming a test pilot. We don't know when this airplane will stall. We don't know how much lift it's generating. But this type of icing tends to be fairly light, if we want to say that. Now, the type of clouds that this likes to form in are clouds usually that are fairly level, so stratus type clouds. You can imagine that because if we have small droplets, stratus type clouds, think of freezing drizzle that will sometimes come out of it. Now, when we get to the larger droplets, big problems start to occur. First of all, let's think a little bit about how we can end up with larger droplets. Well, we actually read this on the slide a few moments ago. To get larger sized droplets, what we actually need is some sort of vertical development. Remember, larger droplets just like we've learned in rain, thunderstorms, to get those, we need some sort of an updraft happening because these heavy droplets need to overcome gravity. So if we get a cloud with vertical development and we have supercooled droplets within it, these droplets will start to coalesce. At the bottom of the cloud, they're little, and as they get to the top of the cloud, because they keep colliding, they end up getting larger and larger. So by the time they're at the top of the cloud, we now have significantly sized droplets. So with these larger droplets, if you are flying near the top of the cloud, if it's a cumuliform cloud, so cumulus, typically that's where you're going to encounter the worst icing, is towards the tops of the cloud. All of those large droplets are suspended up there. So let's now take a look at what these larger droplets will do. So I'm going to erase the leading edge here. No longer stratus. Now we're most likely going to be in cumulus type cloud. And this larger droplet now works its way towards the wing. Well, as soon as it smashes with the wing, it's going to kind of spread out. So there we go, it spreads out a little bit. Now, the next droplet comes in to join in on the fun. It smashes into the wing, and it spreads backwards as well. Another droplet decides to join in on the fun, smashes in, and then it spreads out as well. Now, typically, they will spread and follow, of course, the airflow. Notice as each one of these large droplets strikes the wing, it does not freeze instantaneously. Because it's so large, it has a few moments to flow backwards on the leading edge of the wing. So there's no air pockets here. Absolutely none. So that's going to make this ice a lot heavier. Another interesting thing that it does is, remember, typically, when it comes to the aerodynamics of the leading edge, remember, we have a point called the stagnation point. And what happens is the air decides some of it to go that way, and some of it decides to go that way. Well, the water droplets do exactly the same thing. So what you actually end up with is you actually end up as well with this kind of going like this, and then like that, and then flowing like that. So this will flow forwards, and it will build like that. You actually end up with this horn-like structure on the leading edge of the wing. So imagine, my goodness, when it comes to clear icing, and we have this horn developing, versus, remember how at the leading edge with rime ice, it was just quite simply a spearhead. It's not bad, but think about which one is going to produce more drag. Clear ice is going to produce a lot more drag. It's also going to have a lot more weight to it. Clear ice is also very hard to clear from our wings because it's frozen and it's so solid. All right, so there's some of the basics behind the types of ice. So we'll look at these different types of icing a little bit closer now. We'll look first of all, of course, at the rime ice. So, as I mentioned, instantaneous freezing of supercooled water droplets. It's rough, it's milky and opaque. It kind of looks like the inside of a freezer that hasn't been defrosted in a while. I don't know if any of you have those extra large, say, chest-style freezers. You know, you don't defrost them very often. You pop it open and you look and it looks like there's all this snow and kind of like a hoar frost clinging to the sides. So that's what we get. Typically, as I mentioned, forms in layer-type clouds such as stratus. Now, it's not very adhesive. I mean, clear ice, as you saw, it spreads out and it sticks and it's stuck good. With rime ice, it tends to be a little bit brittle. So that is one advantage for us as pilots. Well, I shouldn't really say icing. Icing really doesn't have too many advantages. But if there's any, it's going to be that, okay, so this one is a little bit brittle. When I activate something like a de-icing boot, because it's brittle, boom, it will shatter very easily. So it tends to be a little bit easier to clear from our aircraft than clear ice. Most commonly, and be careful with this statement because it most commonly results in light to moderate levels of icing. Not always. With many things in weather, it depends. So clear ice. Here we go. You can see actually this very clearly here. Pardon the pun. You can see very clearly here that we've got the leading edge of the wing, and you can actually see right here kind of the stagnation point of that leading edge right through here. Because you can see the droplets have been striking this zone in through here, and then now what's happening is we actually have that water flowing backwards above and below this particular wing. So we actually end up with that horn structure forming. The top picture here, you can see how it's fairly transparent. You can see through that clear ice, unlike the rime ice where it was just not transparent at all. Slowly freezing, that's what clear ice does, slowly freezes to the surface of the aircraft. This is the more dangerous. I mean, both types of icing aren't any good for us at all, but clear ice, as I mentioned to you, is typically more dangerous because it is heavier. It ends up producing more drag. Clear ice as well is often associated with freezing rain, so it collects very quickly. Not good. Now, horns, we talked about those quite a bit, so off we go to the next slide here. All right, clear ice, as I mentioned, freezing rain and freezing drizzle. We talked about the types of clouds where they like to form in. We talked about the tops of the clouds and how those can be the most dangerous when it comes to clear icing. Now, here's something to watch out for as well. Remember that statement, vertical development. So that being the case, right here we have lenticulars are also well known for producing severe clear ice. So that's another type of cloud to watch out for. Very heavy. This can make the control surfaces freeze together sometimes even, and it's unlikely to flake off easily like the rime ice does. So mixed ice. Here's a great picture of mixed ice. It's just a mess, this particular airplane. I often like to kind of look at this because you see this guy here in the parka. Look at how he's just getting blasted. You can see all the fur is just backwards. So that's him with that airflow. I don't know what temperature it is in there, maybe minus 40, but just freezing to death. Look at his buddy over here. His buddy's like, hey, Joe, is it cold in there? You know, he's in the nice warm little room looking through the plexiglass, and this guy has to go out here. Looks like he's holding some sort of a tool or implement to measure how quickly the ice is freezing. Anyways, another thing to notice here too is see where he's standing and there's no ice collecting there. So if you ever want to avoid collecting ice, what you do is you just take your passenger and you stick them out in the front of the leading edge. Don't do that. Don't do that, but this picture shows that it works. Anyways, don't do that. All right, let's move on. Okay, so ice accumulation. There are several factors that have an effect on the rate at which ice accumulates. Now, one is droplet size. You can imagine clear ice being large droplets, it tends to, of course, form at a much quicker rate. So droplet size, we've kind of covered that. The next two are airfoil shape and airfoil speed. Now, airfoil speed makes a lot of sense in that the faster we travel, the more ice we're going to collect. If I'm traveling faster, of course, I'm going to have more molecules that will collide with my airplane. So that makes perfect sense. This one here, though, I can see it catching a lot of people because initially it's like, what? You know, it's actually the thinner airfoils that collect more ice than thicker airfoils. Yes, I said that right. Thinner airfoils collect more ice than thicker airfoils. Okay, scratch your head for a minute, and then to solve the mystery, let's head over to the whiteboard for a moment, and we'll draw what's happening. Now, again, if you've studied some of the general knowledge and aerodynamics earlier on pilottraining.ca, this might suddenly make perfect sense to you. Here's what's happening. Let's imagine two airfoils, both of these airfoils traveling at the same speed. So we will draw airfoil number 1, which is going to be reasonably thin. And then we're going to exaggerate and give ourselves a great big twin otter airfoil, so a very, very thick airfoil. So this being the case, the thin airfoil, remember, what it's doing is it's actually sending out ahead of it at the speed of sound pressure waves telling the air that it's on its way. So, of course, it sends out pressure waves as such, saying, I'm headed this way. So these pressure waves are going to be smaller than the pressure waves here from the large wing. So, in this case, let's imagine, first of all, the thick wing. So now we've got these little water droplets. The wing is heading towards them. Those water droplets enter the pressure zone, and they're kind of like, whoa, something's on its way. So actually what happens is they have lots of advance notice that they need to get out of the way of that approaching airfoil. So they actually end up bouncing around a thick airfoil. Meanwhile, I maybe shouldn't have drawn quite as many pressure waves. There we go, we'll give them 3 pressure waves equally. The thin airfoil, the water droplets headed towards this one, hit the small pressure wave, and they're like, whoa, not enough time to get out of the way. So then, smack. There we go. And we'll imagine that this is maybe clear ice. So, because the thin airfoil doesn't give as much advance warning that it's on its way, it's going to collect a lot more ice. So, thick airfoils collect less ice than thin airfoils. That means things like, think about our horizontal stabilizer. It's basically a very thin wing. Later on, we'll see and remind ourselves that it's an upside down wing, but our horizontal stabilizer is very thin. So that means I'm typically going to see ice forming on my horizontal stabilizer before I will my wing. Other places that I might see ice forming. Let's imagine that I have like an antenna that's visible somewhere. Well, antennas are very, very thin. So an antenna being the ultimate in thinness, it's definitely going to start collecting ice, maybe even before, say, my wing or even my horizontal stabilizer does. So the thinner the surface, the quicker it's going to collect ice. Of course, as we head back over to the presentation now, the faster my airplane is moving, typically the more ice it will collect. Now, for those who move on towards their ATPL and flying jets and things like that, that comes at a limit, because sometimes what happens is once you start to get at very, very high speeds, you have skin friction happening, and it actually heats up the leading edges of your aircraft for you through skin friction, so that might delay some of the ice from forming. Now that said, for those of you who are thinking about smaller general aviation aircraft like your 172 and Cherokee, yeah, the faster you go, the more ice you're going to collect. Droplet size, the bigger the drops, the greater the collection rate. All right, so we've talked about this here. Speed, we've talked about this here. And then droplet size. Now, again, remember, when it comes to developing large-sized droplets, typically we need vertical currents of some sort. So TCU, cumulonimbus, ACC, those are all suspect in terms of developing larger clear ice types of droplets. Orographically lifted clouds. So those on the windward side, as they go up the mountain, vertically climbing, those ones can develop quite a bit of ice as well. Not to mention some of the lee wave clouds, and we've also talked about how the lenticular clouds are specifically suspect. All right, a larger water droplet will be more likely to strike the wing than a smaller droplet. Oh, you know what? I showed you like the pressure wave, but also just think in terms of momentum. The heavier a droplet, the harder it's going to be to deflect it off of its path, right? So that's going to be another reason that it's more likely to strike the leading edge of the wing. Clouds, of course, with high liquid content will also have greater icing intensity. Now, think back to when we were talking about moisture on pilottraining.ca. Remember, the warmer an air mass is, the more moisture it is capable of holding. So what this is telling us is that most commonly, not always, but most commonly, a warmer air mass will be able to hold more moisture. So that means if we have clouds and supercooled water droplets that are hovering around the 0 to minus 10 degrees Celsius mark, those are going to hold a lot more water than a cloud at the minus 40 degree mark. Most of the time. There are cases with cumulonimbus and stuff like that where that general rule can be seemingly altered. But that said, generally, clouds in warmer air masses are more suspect in terms of developing greater amounts of icing. Now, you're flying along, and as I mentioned, typically you want to avoid icing. Doesn't matter what type of an airplane you fly, you typically want to totally stay out of that icing. You're flying along, and you look out your window, and you're like, I'm collecting ice. All right, well, at what intensity? There's 4 intensities for reporting. Now, when you look at these intensities, I also want you to keep in mind that, again, this can be relative. I mean, if you've got your smaller, say, Cessna Skylane or something like that, and you're accidentally encountering some ice, you're going to be pretty much stuck in that ice, and you might call it something like, say, moderate. Meanwhile, somebody like a 737, they fly through the same cloud, but they've got so much power that they blow right through that cloud. And they only pick up a little bit of ice, so they might report it as light icing. Sometimes when you look at reports of icing in practical terms, you need to be aware of what type of aircraft was reporting it. Your smaller airplanes are typically going to be more affected by icing than some of those larger aircraft. Now, before I discuss each one of these individually, I do want to show you this diagram over here at the right. And it seemingly has nothing to do with icing intensity, sort of in a way. Mostly this diagram here is just to show you some of the key temperatures that encounter or happen with icing conditions. So we've got the 0 degree mark here, surface down here. And you can see that if I'm below 0 degrees Celsius, I'm definitely not going to get any icing. Well, I shouldn't say definitely not, but the odds of icing, if it's hovering close to 0, yeah, but if it's above 0, 1 degree, 2 degrees, way less likely. So as long as I can stay below the freezing level, I am going to be safe. Once we reach the 0 degree level, though, if we have lots of supercooled water droplets, well, the icing definitely can start. So between temperatures of 0 and minus 10 degrees Celsius, even to a degree up to minus 15, those are typically the worst temperatures to encounter water droplets. Now, that doesn't put you in the clear between temperatures of minus 15 and minus 40. Supercooled water droplets can exist up to temperatures of minus 40. Now that said, once we hit minus 10, you can actually see that we do start to have some ice crystallization starting to happen. Now, interestingly enough, between temperatures of 0 and -10, if we have supercooled water droplets, ice crystals don't really tend to form. It's kind of difficult to get them going. Once we hit -10 though, some of them do start to spontaneously freeze. Those water droplets will freeze, they'll turn into ice crystals. And then once that happens, we do end up with this mix of ice crystals and supercooled water droplets. Usually what happens, if we can manage to get this crystallization process going, it's going to start to absorb some of that moisture. So you can see at the higher levels, we actually end up with less and less moisture. By the time we hit -40, then quite often we have entirely ice crystals. Not always, but quite frequently. This here is showing you the danger of those vertically developed clouds, because they can take that cold air, move it up. All of those supercooled water droplets, they can move them up rather rapidly, and see how we really don't have any crystallization going on through the entire temperature regime. It just gets moved up so quickly that we end up with these supercooled water droplets not really glaciating or turning into ice until very extreme altitudes. Again, with cumulus type clouds, we would expect to encounter quite a bit of icing towards the tops. Now as we have that anvil starting to form, okay, now we definitely have glaciation going on, and that's why we end up with that high cirrus looking anvil. All right, so let's come back to trace, light, moderate, and severe. Make sure you know and memorize each one of these for your exam. Trace. In this case, ice becomes perceptible. The rate of accumulation is slightly greater than the rate of sublimation. It's generally not hazardous unless if you stay there for an extended period of time, an hour or so more. Now, note of caution here, we had to put this picture in somewhere and it fit in here best. This photo is not an example of trace icing. It is a photo of icing accumulated during tests by NASA. More details are available by watching the presentation. Okay, so as I mentioned, this technically, because as you look at this, you might be like, well, that doesn't quite look like exactly what you showed us earlier, Aaron. And that's because this was actually on the vertical stabilizer for this particular test. So if you took this and you rotated it 90 degrees, now you can imagine that airflow is coming from where I'm standing and flowing kind of upwards and then kind of across this particular airfoil. So that's what it looks like more on a vertical stabilizer. Again, that is not trace icing, definitely. I think that was in the ice machine for about 30 minutes, if I remember correctly. So, you know, we're starting to talk about more moderate to severe levels of icing. All right, so trace. You got this memorized? Good. Let's move then on to light icing. In this environment, the rate of accumulation may create a problem if the flight is longer than 1 hour. And once again, a disclaimer, caution, the photo is not an example of light icing. It is a photo of icing accumulated during tests by NASA. More details are available by watching the presentation. So now what they've done is they've taken that last picture and they've actually subjected this to laser measurements. So they can see the exact depth and they can see almost, it looks like at some points, individual crystals. And as they monitor that, they can actually see those crystals forming and how it is that they coalesce and end up designing all of these weird and wild shapes. So, moderate icing. In this case, the rate of accumulation is quick enough that even short encounters will be potentially hazardous. De-icing or anti-icing equipment will be required to clear it, and a diversion may be necessary. Now, when it comes to looking at your charts, say the GFA, specifically the icing, freezing, and turbulence charts, icing is typically in, well, I should say typically, it's always in this, here you go, blue color right here. So blue, stipples, and that is on the freezing and turbulence chart. Now don't forget, icing, when we see it on the clouds and weather chart, is in a red color. Okay, so don't mix these up on the exam, because then when you go to the icing, freezing, and turbulence level charts, well, you can just barely see a little bit of red right here. On this chart, then that's turbulence now. Okay, so watch out for that gotcha. So this here is telling me on the GFA I've got mixed icing. It's telling me here as well that I've got moderate, so that's what the 2 bars are for. And then it's further telling me that the icing is occurring from 4,000 feet up to a height of 15,000 feet. Okay, so that being the case, how would we get around this? Well, most of us cannot go 15,000 feet or above in our small little airplanes. So 4,000 feet, maybe I could go under it. Stay out of the clouds. My bet is that the cloud base in this particular case is at 4,000 feet. So stay below the clouds. Be aware, though, that there might be lowering ceilings ahead of you. Study that weather very carefully. Okay, so let's move on to severe. And in this case, there we go. This is an actual, you can see the vertical stabilizer now in this case here. They've left this in here for an extended period of time. It's now warm enough that this poor guy who was in the parka can actually flip it back, and now he's going about measuring that ice. So severe icing is a case where the rate of accumulation is fast enough to render de-icing equipment or anti-icing equipment useless. Doesn't matter how much protection you have on that plane, it's not going to happen. And it's just not going to happen. An immediate diversion is necessary. So GFA, here's what this looks like. We've got the bars that are showing now severe icing. And then we have, it's telling us from the surface, so from the surface in this case up to 3,000 feet, that is where the icing is going to be the worst. Now, if you encounter icing conditions, first of all, remember the ingredients that I gave you at the beginning of the presentation. Avoid it to begin with, please. Stay out of locations with visible moisture if the temperatures in particular are 0 degrees Celsius or less. Now that said, if you are a VFR pilot, staying out of visible moisture should be a given. You're not allowed to fly in clouds, and you know, when it comes to rain and snow won't really create icing because it's glaciated, but when it comes to rain and clouds, you're supposed to stay out of them anyways. For those of you who are IFR pilots, do your best to eliminate one part of that equation. Done deal. You won't get icing. All right. But, okay, so you do encounter icing. Maybe it wasn't forecasted. Happens lots, to be honest. Particularly so in the springtime and in the fall time. Those transition months where we sometimes have freezing levels that are starting to get lower and closer to the surface of the earth. Make an immediate decision. Now, probably what we should have done was changed the order of these recommendations. First of all, this one here, if you're in a light general aviation aircraft and you're starting to collect ice, usually this option isn't the best. Climbing. Descending might be the best option, particularly if you know that there's no terrain below you. Going back is probably the best option. Turn around and go back. Now, I actually want to look at this one here a little bit closer, this recommendation, and tell you why or why not in terms of it being a good idea. Okay, so let's head over to the whiteboard and I'll quickly draw why we have to carefully consider whether a climb is a good idea or not. Now, first of all, before I erase this, I just want to look at this again. Use this and let's say that even though it's a thicker airfoil, let's say that the icing conditions are such that we know that we have collected a lot of ice. So here's what's going to happen. We're going to end up with this ice. We'll say it's clear ice in this case. So we've got this, and maybe we'll draw kind of this classic. There we go. So we are full of ice. Now, in a little bit, what we are going to learn is that, okay, so ice, that is going to add to the weight of my aircraft. Then, now, imagine that I'm airflow approaching this wing. Now, I kind of try to go up and over the wing. I get stopped here, and now I become very turbulent very early. So, what's that going to do to our lift? Well, that's going to be really, really bad because our lift is going to start to decrease as well. So we have the weight happily increasing as we continue to collect ice. We have the lift decreasing. But now think about our drag. So our drag, because of all this rough ice, is going to start to become greater and greater and greater. Our thrust, meanwhile, because it's trying to offset the drag, our thrust is going to become much diminished as well. Now, for us to climb, what does an airplane need to climb? Well, if you can remember back to your basic training, to climb, I need this: excess thrust. You can think back to the lift and drag curves and the power required curves, and maybe you'll start to be able to figure that out. But just for now, remember, to climb, I need excess thrust. But if I'm collecting ice, any excess thrust that I had prior to collecting ice, and it's not a lot in these little airplanes, it's disappearing. So I'm going to find that my ability to climb can start to become pretty close to nothing. Nil. Zero. Okay, so knowing that, let's start to move into a little bit of a diagram and thinking about, well, is it really a good idea to climb? First of all, I know that I have less available excess thrust, so I am not going to climb as well. What I next would need to carefully consider is we'll do a profile view here. So put in a little bit of terrain, maybe a little bit of a pine tree here. And let's imagine that we have a case where clouds are here. I have, in this case, the freezing level is maybe, say, somewhere, I thought it was a little bit higher in the clouds. So maybe we'll say 0 degrees Celsius here. And because I'm an IFR pilot, I am legally flying in the clouds. And I actually encounter the freezing level at a level slightly below where I thought it was. So now I start to collect ice. The decision, climb or descend. Well, here's what I would partly base this decision on. First of all, I know, okay, in these little light planes, as I collect the ice, less and less thrust. My ability to climb is going to become compromised. If I knew for sure where the tops of the clouds were, let's say maybe they're at, I don't know, we'll say the base is here where maybe say 5,000 feet. And then we'll say that maybe the tops here are at like 8,000 feet. Meanwhile, I've been cruising, because I'm cruising easterly, so we will say that IFR altitude would be 7,000 feet. So 7,000 feet, I know that the cloud tops are above me, 1,000 feet up. Okay, maybe I might consider going up on top. I might. However, what if these tops were up at, say, 12,000 feet? Well, for starters, I don't have oxygen, so I can't go up there anyways. But maybe let's just say 9,000 feet for the sake of putting out that don't need oxygen argument? I don't know. That's a tougher decision. Might depend on how much ice I've collected. But I would be way less likely to climb now than I would be to descend. Descend below the freezing level. Or maybe even, if I have enough room from the terrain, watch out for the terrain below. I might even descend below that cloud base and then fly in the clear air. All right? Typically, climbing is not a good idea because of our reduction in excess thrust. If I'm going to climb, I better know where the tops are, and I better know that I have a good chance at reaching those particular tops. All right, so please, people, with your little airplanes, keep that in mind. Meanwhile, if I'm in a 737 or a Q400 or a King Air, maybe because I have a lot of extra power, I might consider going up top. Okay. Definitely remember to activate any de-icing equipment that the aircraft contains, and pitot heat is one example of this. Hey, looks like we've already covered some of this when I was over at the whiteboard. Dangers of icing. All right. The effects of icing really boil down to this. Absolutely rotten aerodynamics. There will be an increase in drag and weight. There will be a decrease in lift and thrust. Okay, it all makes sense. I showed you this on the whiteboard. The more ice I collect, the more of this I will have, which is bad because ice weighs something, and then the less of this I will have because the flow over the top of my wing becomes more and more turbulent and it separates from the wing earlier. Therefore, I am becoming a test pilot. The drag gets worse and worse as I collect more and more ice. And then the thrust available becomes less and less as well. And we'll discuss how the thrust becomes worse. There's many ways that it does. So we'll take a look at some of these specific aerodynamic reasons right in the next few slides here. We have more drag, so that requires more power to sustain flight. This is caused by those rough surfaces of the ice. Now, imagine our engine and the thrust it's going to produce. First of all, it's trying to overcome the drag, so that means that it's going to have less thrust available. But then as well, think about this. Our propeller is an airfoil. A lot of people forget this. So it's churning through that air at 2,200 RPMs, which is a very fast speed, and it is a thin airfoil. Okay, with what you've learned, put those two things together. What does that mean? Yeah, our propeller is going to be likely collecting ice as well. If our propeller is collecting ice, it's a wing generating thrust in the horizontal component, so now it's not going to be able to move as far forward, and it's going to be generating less thrust simply for that reason. We could also have, and we'll come back to this later, we could also have our air filter getting plugged. So if our air filter starts to get plugged due to all of this impact ice, guess what's going to happen to the engine itself? It needs air. Remember, 14 to 1, 15 to 1 typically are the ratios of fuel to air. Well, I should say air to fuel. There we go. 14, 15 to 1. Yeah, air to fuel. We need more air than we need fuel. And if we start starving the air going into the engine, guess what our engine does? It's like you. If I kind of asphyxiate you, well, that's not, you can't breathe. Engine does the same. Less thrust. Okay. It is likely too, if you're flying a turbine engine aircraft, that you might end up with foreign object damage. And this is where that ice starts to flake off. It falls backwards into all of your fans and critical components that are in your engine, and yeah, it does damage. Not as much of a problem for those of you who will be flying piston-type aircraft. Okay. Whoa. Wing effects. Lots of wing effects. Icing alters the shape of the wing, which will cause an increase in the stall speed. You basically become a test pilot. You saw on the whiteboard how the airfoil shape changes. I can guarantee you that NASA has probably not tested that specific form of airfoil. So, that being the case, you have no idea what it's going to do. When will it stall? I don't know, but I can tell you that it will stall at an earlier speed. Okay, so if you are used to it stalling at, say, 45 knots, it's probably going to stall at 80 knots. Now, in terms of the angle of attack, notice this as well. It's going to be decreasing. So, I actually pointed at the wrong spot there earlier. Sorry, everybody. Stall speed increasing. There you go. That's what I meant to point at. And then the stall occurs at a decreasing angle of attack. So, your airplane, what does it typically stall at in terms of angle of attack? Okay, hopefully some of you responded 16 degrees to 18 degrees. Good. Once we have ice on our wing, it will stall at an angle of attack of, say, maybe 12 degrees. I don't know. I don't know where. I don't know when. I can't tell you. All I know is it's going to be a lower angle of attack. In terms of speed, as we discussed, it's going to be a faster speed. Now, what this means to you practically as well is that you might stall and you won't have any indication because none of your stall warning devices will go off. Why not? Well, remember, if you read through your POH, most aircraft have a stall warning go off approximately 10 knots prior to the actual stall itself. They want to give you some warning. So if your airplane stalls at 45 knots, typically the stall warning devices will go off at 55. But you've collected so much ice that now the airplane is going to stall at 80 knots. Does your stall warning device ever go off then? No, it does not. So keep that in mind. Now this one here is a little bit more technical to describe. Deteriorating trim effectiveness. Remember, the tail surfaces being thinner collect ice more efficiently than the main wing in most aircraft. Less lift from the horizontal tail requires more elevator, which could then end up running out. Now, you also need to remember that the main wing, which can stall, the horizontal stabilizer out back is also a wing that's been flipped upside down. And yes, your horizontal stabilizer can stall. And sometimes, in certain types of aircraft, your horizontal stabilizer can stall before the wing stalls. Weird. We'll come back to that in just a little bit, because the effects of a tail stall are very important to recognize, and you will need to know the recovery procedure for such an eventuality. All right. More effects of aircraft icing. Asymmetric shuddering and vibrations due to one propeller or rotor blade shedding ice. Okay, talked about that in terms of the propeller collecting ice. So imagine one side of your prop sheds a little bit of ice and the other doesn't. Not so good. I mentioned this earlier. Control surfaces may freeze in place. Wing flaps can be damaged. We talked about control surfaces freezing in place, so now you try to put your flaps down and you damage your flaps, or maybe only one comes down and not the other. That's really bad. Really, really, really bad. Putting flaps down in icing conditions also significantly changes my airfoil, which has already changed a bunch to begin with. So the general rule, when you've got lots of ice, it's probably not a good idea to put your flaps down. And once we get to tailplane stalls, you'll also see another reason why it's probably not a good idea to put your flaps down should you have encountered ice. The landing gear may freeze in place. I don't like that either. Or may be damaged by movement in icing conditions. I don't like that either. I kind of want that gear to come down. Does give the firefighters a pretty good show, though, if sparks are flying everywhere. And that's why they foam the runway, by the way. Okay, so don't make the firefighters foam the runway. All right. More. Fuel vents can become blocked. Okay, fuel vents become blocked. Well, we don't typically have any sort of a heating device to those. So if the fuel vents become blocked, well, our engine gets starved of fuel now. Engine quits. Not too much you could do about that one. The pitot tube can become blocked. And boy, make sure you remember the rules for this. I'm not going to go over them here because we cover them in the airspeed indicator and in the pitot-static systems, but you better know what that system will do should it become covered with ice. Either the pitot tube or the static port being covered. Completely obscured cockpit vision due to ice on the windshield. Yeah. I had that happen once to me. Not once, but, well, a couple times. Not in the forecast. You're flying below a base of clouds in the fall. You know that the temperature outside is less than 0 degrees. And you're well below the base of the clouds, but all of a sudden you start to get some freezing rain or drizzle falling. It's like, whoa, that wasn't in the forecast. So now your cockpit becomes completely glazed over. And it kind of feels like you're trying to look through stained glass. Now, that said, have you ever read the POH for many of these light aircraft and what they say should you encounter icing? Well, we talked about turning on all of our anti-icing devices. So you turn on your pitot heat, whatever you got, you open up the cabin air as wide as you can to blast as much heat as possible onto that. Maybe as well, lean out the mixture a little bit so the engine runs a little bit hotter. Carb heat on just in case if you're afraid of maybe some of that impact ice occurring. And then one of the things that many light planes say as well is to attempt to reach outside and scrape the ice off of the front of the windshield. I will admit I tried that once and only once. The reason being, it's kind of almost impossible to reach all the way out there and start to scrape off that windshield while you're trying to fly the plane. The other reason is once you stick your fingers out there, they get kind of cold. I was worried because they were starting to turn blue and I thought they might all fall off. Okay, the final thing is the only thing you've really got is like a debit card or a credit card or something like that. So you're kind of reaching out with it, you're trying to scrape it. You're like, maybe using this debit credit card isn't the best idea. And then suddenly it catches in the slipstream and away it goes. No, that didn't happen. But you're thinking about all those things. It was really when my fingers started to turn blue. And it didn't work good anyway. So ignore that part in the POH probably. Okay. Reduction in radio reception may cause antennas to vibrate and break off. Small airfoils, they collect a lot of ice. So now you've got this really wobbling radio antenna and you're wondering why everything's crackly and staticky. Suddenly everything goes quiet. Antenna departed. Could happen, has happened many times. Now, in some aircraft manuals, it's recommended that we do not bank any more than 5 degrees should we have encountered ice. Again, this is because of the increase in stalling speed. So if we bank a little bit, and even the smallest amount of tugging back, we could potentially stall our aircraft. So watch out for that rule. Okay, so icing checklist. This really is like how to avoid icing. Before your flight, check for any icing conditions. That doesn't mean that they won't happen. Sometimes things happen that aren't forecast, just like myself flying there. Get a weather briefing from the forecaster in that area. Ask and check for PIREPs. Can you plan your route around any of the known icing? All right, so use the two-pronged strategy of stay out of visible moisture and or stay out of temperatures below 0 degrees Celsius. Make sure your aircraft is clean before you take off. That should be common sense, I hope. We'll talk about this a little bit more in a few moments. Is your aircraft certified for flight through icing? Okay, this statement here, I just want to add a little bit of a disclaimer here. Just because you have an airplane that is certified for flight into icing does not mean that you want to purposely go flying into icing. De-icing and anti-icing equipment is simply there to buy us a little bit of time. It is not there for us to say, hey, yeah, I can go into any icing and stay in there indefinitely. Bad decision. This de-icing equipment or anti-icing equipment is simply there should you encounter those conditions for a limited time. And it might get you some additional resources to exit those conditions quickly. So keep that in mind. It does not give you a blanket, yeah, fly into this. Of course, if you must do your best to avoid, I should say you must do your best to avoid, change your altitudes, maybe postpone your flight indefinitely, maybe divert around those locations where it looks like icing is potential. So, yeah, do those things. Now, if you do happen to encounter some icing and you notice that your de-icing equipment is starting to lose its effectiveness, get out. Remember, it's mostly for buying yourself some time. Avoid abrupt maneuvers if your aircraft is starting to collect ice. We've talked about stalling speed. We've talked about turning and banking. Banking increases the stall speed. Remember that 5-degree rule in terms of bank for many aircraft that exist. Remember, our stall speed is going up. When you approach, if you have collected ice, when you approach, we talked about maybe don't put the flaps down, okay? Might be a good idea as well to approach with some extra airspeed. Extra airspeed will give you a little bit of extra margin from your stalling speed, right? If you encounter icing, file a PIREP as soon as possible, either in the air or when on the ground. A PIREP is the most reliable means of updating the weather for the pilots around you and as well for the forecasters who need to design a new forecast. They'll be like, whoa, there's icing out there. Okay, didn't expect that. Now, icing is tricky. It can change really fast. I mean, you might encounter icing, and then as you go ripping through that cloud, because you've become the biggest condensation nuclei in history, suddenly all of that water vapor behind you suddenly starts to crystallize. You got the cascade action happening. So an airplane that's flying behind you might experience actually different conditions. Don't count on it, but it is interesting how quickly icing conditions can change. All right, remember these rules about clear ice. Cumulus clouds, typically. Try to avoid them, whatever the season. Typically, avoid the tops as well. The worst icing in cumulus clouds tends to occur between 0 degrees Celsius and 10 degrees Celsius. When it comes to stratiform clouds, typical worst temperatures, minus 10 Celsius to minus 20 degrees Celsius. Get out of them, and as well, do whatever you can to activate your anti-ice or de-icing equipment. So let's start to talk about some of our de-icing equipment and as well our anti-icing equipment. Now, it's important that you recognize the difference between the two. When we talk about de-icing equipment, we're talking about equipment that removes ice that has already formed. When we talk about anti-icing equipment, we are talking about equipment that is proactive. We have it turned on prior to us entering potentially icing conditions, and it is now going to prevent the formation of ice. Which do you think is more valuable? In most cases, yes, the anti-icing equipment. So let's start out with some of the de-icing equipment. And one example is here. You can see this wing right here, and you can see the leading edge. Now, this leading edge, it looks like it's all black because maybe somebody painted it. That's not the case. What this actually is this is known as a de-icing boot. And essentially, what it is kind of like a balloon on the front of the leading edge of the aircraft. So, what it will do is, once you've started to collect some ice, you as the pilot flip a switch in the cockpit, and once you flip that switch, this suddenly inflates, like a big balloon. So the idea is that any ice on here will suddenly shatter and go clear of your wing. All right, so de-icing boots, talked about that right there already. So now let's talk about some of the anti-ice equipment. In this case, remember, equipment that is designed to prevent ice from collecting in the first place. This airplane has a really nice example, and originally you might look at this, you might be like, hey Aaron, that's a de-icing boot. No, this one actually isn't. I know it's black, and I know it's on the leading edge of the propeller, but what this actually is it's a heated element. So if you are worried about the potential for encountering ice, you would actually turn this on. This heated element, of course, is going to heat your propeller, particularly so the leading edges, and that will help prevent ice from forming. Other common places that you'll see these electrical type of heaters is sometimes on a windshield of an aircraft. You'll see this little square patch that almost looks like a heads-up device. And in that case, no, it's more so for anti-icing. Okay, so electric heating, commonly used on windshields and propellers. Jet aircraft have a unique way of having anti-ice, and that is that they will actually use hot air from the engine and they will blast it along the leading edge of their wings and or horizontal stabilizer. Now, the disadvantage to these are that they absorb a significant amount of power from the engine of the jet, and as well, typically what happens is they heat the wing up so much and or the horizontal stabilizer up so much that they actually can't often be used during ground operations or at low levels and slow speeds. You would literally start to melt the wing. All right, this airplane here, this stationaire, it actually has, and it's too bad that it's a little bit hard to see, but it actually has something known as TKS. What this system does is, if you could see it really closely, there's actually little holes all through here. And what it does is, typically somewhere in the fuselage or somewhere in the wing, you actually have a great big container of essentially antifreeze. And what you do is, in this case again, a switch in your flight deck, you flip it on, and then all of that fluid moves from the container up towards the de-icing zone here. So this fluid will then be pushed out of these little holes in here. So as that fluid gets pushed out of these little holes, what it does is it then seeps and it runs backwards along, in this case, it's the vertical fin. We typically will mount these as well on the leading edge of the horizontal stabilizer and, of course, the leading edge of the wing. The really nice thing about this is it not only protects the leading edge, but because this fluid runs backwards, it typically will as well cover the surface behind the leading edge. So you have a fair amount of ice protection from a TKS system. The disadvantage is whoa, they're heavy. I mean, antifreeze is heavier than water, and that being the case as well, they do eventually run dry. You can only pump a fluid through these leaky holes for so long. All right. Now, frost, this typically doesn't occur while in flight. But that said, we do need to know about it for the exam. Remember, if we have frost forming, that's because the aircraft is at a temperature that is below the dew point of the surrounding air. When we get frost on our wing, we do need to remember these two facts. Our lift is reduced by 30%, and our drag is increased by 40%. Now, this is for a layer of frost that is approximately the consistency of medium to coarse sandpaper. It's a very common knowledge item on the exams. If we have frost on our wings, the consistency of sandpaper, how does it affect the lift and drag? Lift 30% reduced, drag increased by 40%. Now, another type of icing that might not be immediately obvious is for more so people who fly at high altitudes. And this would be something known as cold soaked fuel. Now, if you're commercially studying for your exam, you definitely need to know this at the CPL level. Recs and PPLs, not so much. But what I'm going to do is I'm going to actually head back over to the whiteboard for just a moment, and I'm going to sketch what happens with cold soaked fuel. So in this case, I can actually erase the clouds up here, but I'm going to leave the terrain. Let's imagine that you happen to be somebody who is flying extremely high. So we will say that initially, maybe you're flying at, I don't know, we'll use, say, 35,000 feet. Doesn't need to be quite that high. But imagine up here the temperatures. They can be, if this is, say, the tropopause, they could be, say, minus 40 degrees Celsius, somewhere all the way up to about minus 60 degrees Celsius, depending on the season. So meanwhile, you and your airplane have been flying at these super cold temperatures. So your airplane cools down to minus 40 or minus 60 degrees Celsius. Meanwhile, what's in your tanks? You've got fuel in your tanks. So your fuel is probably going to start cooling down significantly as well. So now here's what happens. You, in your airplane, descend. And as you descend, we're going to imagine that as we get closer to the surface of the Earth, we've got warm air and humid air. We're going to say that maybe it's plus 30 degrees Celsius and the relative humidity is something like 97%. It's a scorcher. Not a very comfortable day. So as your airplane descends in through this warm, humid air towards the airport environment, what's now going to happen is particularly around the fuel tanks. What's going to happen is shortly, maybe as you're in flight, coming in on your approach, now you land, and the airplane sits out there for an extended period of time. So we're on the ground. The airplane, of course, starts to warm up to the ambient outside air temperature. But what about the fuel in your gas tanks? It's going to stay at those cold temperatures. So now what will happen is if you were to look at a side view or a behind the wing view, so we'll draw a small wing here, then you can imagine if you'd like the fuselage here, fuel tank going into a significant depth, all that fuel in there. What's going to happen is as this warm, moist air starts to come in contact with your airplane, and then right in here, remember, this is going to be minus 30. This section here is going to cool and ice up because it's still at minus 30. So you're going to have a patch of ice right over top of your fuel cell. Quite often, you will also end up with another patch of ice just below the fuel cell. That is cold soaking. When you end up with the ice being on the bottom or top of your wing around the fuel tanks. Okay, so we'll head back over to the presentation now. All right, so the rule is when it comes to takeoff, notice this rule here frequently appears on the exam. If you have frost or ice on the top of your wing due to cold soaked fuel, you cannot take off. However, an interesting sub-rule to this that sometimes catches people on the exam is that if the cold soaking is only on the bottom, then you could take off. All right, so keep that in mind. All right, now for those of you who are an ATPL, this is a bit of icing that you do need to know. Frost adhering to the underside of the wing with a grain growth from 0.01 to 0.015 inches in diameter will have no major effect on lift. However, it will increase the second segment climb, limiting weight penalty. All right, so keep that in mind if you are an ATPL pilot, those rules right there concerning frost on the underside of a wing. All right, everybody else doesn't need to worry about that. Now, impact icing, we have covered this a little bit, airframe icing, impact icing. This typically occurs over the intake air filter on both fuel-injected and carburetor-equipped aircraft. In this case, what we have is we can zoom in here on this particular diagram for a moment. As you know, you've got your air filter right here. So imagine that this starts to cover up with ice. We've talked about the effects on the engine, less thrust. Don't forget, you have a little thing in your airplane called carburetor heat. If I pull the carburetor heat, what's now going to happen is instead of the air coming in through here to feed my engine through the air filter, it's now going to come in through the inlets on the cowling. So I can still feed my engine air. However, remember this is unfiltered. Typically, it's not as big of a deal at high altitudes, but it is possible, you know, that even these could start to become plugged too. That would be really bad news because then there's really not much I can do at all if this is already blocked. If these start to get blocked as well from icing, my engine could potentially start to overheat and definitely starve from lack of air. We'll zoom back out. Now, if you are flying a fuel-injected engine, you have something known as alternate air. So in that case, you would pull the alternate air on, right? Can also lean the mixture a little bit if your carb heat is going to be used continuously. Remember, carb heat enriches our mixture, so lean it out. A little better temperature, and then as well, a little bit more power. Okay, I talked about that. So we'll move on to aircraft icing and the cars. Now, the cars tell us that we cannot take off if we have ice adhering to any of our critical surfaces. What are those critical surfaces? Those are anything that generates lift. That's the simplest way to think of it. All right, so wings. Those generate lift. Yeah, so wings would qualify as a critical surface. What about control surfaces? Do they generate lift? Sure they do. I mean, you pull back on your elevator, it causes the, or pull back on your control column, it causes the elevator at the back to go upwards, which is going to change the amount of lift that your horizontal stabilizer is generating. Ailerons, same thing. They change the amount of lift that each wing is generating, right, and cause us to bank. Rotors and propellers. Propellers generate lift in that direction. Horizontal stabilizers, vertical stabilizers, yes, those generate lift. Now this one here sometimes throws students. Upper surface of the fuselage in a rear-mounted engine. Scratch your head a little bit, and why is that a problem? Well, you know how earlier I mentioned that typically piston pilots don't need to worry about foreign object damage? Think about this, though. If you happen to have an airplane with the propeller at the back, let's say that you're flying along and you collect some ice on the top of your airplane and it suddenly sheds. Where's it going? Backwards. What's behind you? Your propeller. What's your propeller likely going to do when it counters all that shattered ice? It's not going to like it very much, not at all. Okay, so that's why that's important. Any other stabilizing surface on an aircraft. Okay, so this would include somebody who maybe flies like a canard. All right, a canard, you've got that stabilizer kind of out front, right? That would qualify as a critical surface. It's generating lift, so there you go, that qualifies. Know these, by the way. Here's the official CARS reading right there. And then here's the CPL rule about cold-soaked fuel. If frost is adhering to the bottom of the wing as a result of cold-soaked fuel, a takeoff is permitted, but it must be performed according to the manufacturer's instructions. Okay, keep those in mind, everybody. Now, when it comes to icing, a visual inspection of all critical surfaces is mandatory before takeoff occurs. That is why we do a walk around. Now, for those who are studying the commercial or ATPL segments, if you happen to be operating an airline, your inspection has to be done by somebody who is qualified. That would be somebody who is, well, the PIC, of course, a flight crew member who has been designated by the PIC, or a trained person designated by the operator. So any one of these can check for icing, and then they would report what the current conditions are of that aircraft. So a few more tips on how to avoid icing. Stay out of the clouds and visible moisture when the temperature is below freezing. Remember that fronts and low pressure systems are obviously associated with clouds. Know what the freezing level is. In this case here, we have a diagram where most of the freezing is along this particular cold front. Most of the icing conditions have been forecasted along this cold front. So that being the case, definitely you don't want to fly directly from A to B because you're going to put yourself into icing conditions for an extended period of time. I know it's going to take you a little bit longer to get there, but if you go through the front clear of the areas predicted for icing, and as well punch that front at as close as possible to a 90-degree angle, you're going to be in it for as, well, little as possible, right? So the best way to be would be flying from A to B. Now, this section here goes into a little bit of thinking before you go. There's many different scenarios that could be worked on through this particular case here. And what we'll do is we'll just zoom in on this just a little bit. So it really would depend on the type of flying that you're doing as you look at this chart here. I mean, if you're flying IFR, well, there's some decision making here definitely that you need to go through. If you're flying VFR, this might be a flight that is really not very possible. So looking at it, what we have here are, first of all, the freezing levels. So you can see 2,500 feet here. You can see 5,000 feet, 7,500, and then 10,000 feet. So they're listed at 2,500 foot intervals. Way up here, I have icing, or the freezing level at the surface. I don't have icing, but I have the freezing level at the surface. So let's imagine that we're going to try to do something like this. Take off from southern Alberta in this location here and kind of maybe head towards Lloydminster, Alberta, or Saskatchewan, whatever you want to call it. So in this case, what we now have is definitely a cold front that's approaching us. And we just said that rule of trying to go through the front at 90 degrees, so that looks like that's doable. But there are several concerns. I mean, as I look at this, I can see right away it's telling me mixed icing, moderate, and then it's telling me from heights of 4,000 feet to 16,000 feet. Okay, now I didn't pull out the clouds and weather chart for this, and we probably should have. But my guess is that when I look at this set of numbers here, that if I looked at the cloud and weather chart, that I would see that the base of my clouds today is at 4,000 feet, and then the tops are at 16,000 feet. Notice the freezing level. 5,000 goes to 2,500. So of course the freezing level is going to reduce as I get closer and closer to my destination. That makes sense. So if I'm near or in cloud, if I'm IFR, and I'm below the freezing level, I'm probably going to get moderate icing. So what would be some strategies here? Well, going above it, 16,000 feet, that doesn't really look very practical, does it? Particularly in our smaller planes. Maybe if I've got a King Air or something like that, and I can fly over top of it, yeah. But in a 172, 152 Diamond, probably not going to happen. So I got to go below it. All right, maybe that can be done. I mean, the freezing level isn't that high here, though, 2,500 feet. I'd probably need to look very, very carefully at the actual cloud heights here. Are they 4,000 feet? Okay, good. I can stay out of the cloud by flying at like 3,500. But then I also need to ask myself, what about the terrain out here? And if I'm flying at 3,500, and let's say maybe unforecasted, any of these clouds in here starts to drop some freezing rain. Well, at 3,500, I'm definitely in those freezing temperatures. They go down to 2,500. So goodness gracious, that's going to be a challenge. Maybe, again, the terrain. I'd have to take a quick look at the CFS too and see what the actual terrain heights are out there. I mean, some people might say, well, Aaron, just fly 2,500 or below. Okay, how high are them hills once we get close to Lloydminster? You might not have enough space or very little space. All right. So if I'm a VFR pilot here, this is looking like it would be a challenging day to try to do this flight. It might even be best just to stay home. Golly, even for those who are IFR, no guarantees, because once you're in this cloud and you hit that freezing level, 4,000, you're probably going to hit ice in that case too. So this one is kind of a very tricky scenario to think through. All right, we'll zoom back out. And then by all means, avoid freezing rain if it's predicted. Just stay away. Winter warm fronts are really bad for freezing rain. You probably remember this diagram from the fronts section on pilottraining.ca. So that being the case, remember it and know that you're just going to be asking for trouble if you try to fly through one of these winter warm fronts. Here's an example of a winter warm front, specifically a winter warm upper front that's happening in Alberta as it rides over the mountains a little bit. And I can just see all sorts of bad stuff in here. I mean, look along the warm front here, moving this direction. Right away I see freezing rain. I see ice pellets. I see A here for the A box, the comments box. What does it say? South of warm front, precipitation is 4 to 6 miles in freezing rain, pellets, and mist. That's just bad news. When I look at the icing and freezing turbulence chart, move over. Oh, remember how I said blue on the turbulence charts? And then look at here how it's on the clouds and weather charts, how it's red, this area of icing. Keep that in mind. Don't mess those up. So here again, looking back at the amount of icing that I've got, wow, severe icing. Right from the surface to 3,000 feet. Clear icing due to freezing rain. That is just bad, bad news. I mean, outside of that, just ahead of the warm front, I've still got problems. You know I'm not in the freezing rain, but I've still got moderate icing from 4,000 to 15,000 feet. Anywhere that I've encountered clouds above the freezing level from 3,000 to 7,000 feet. I mean, this just is not a really nice looking sort of a day at all. So, yeah, those who are kind of in the area of Alberta there on this particular day, yeah, not the best day to go flying at all. Unless you got a powerful airplane that, can take off and get ahead of the front and get through most of that icing, but not going to happen in your 172 Cherokee. Not a good idea. Okay, so a little bit more avoidance. PIREPs, we've talked about reading those. Don't forget to consider, I talked about this earlier, what type of airplane is reporting this icing intensity. The more powerful the airplane, the faster it is, the quicker it can blow through those layers of potential icing, right? Okay, so keep that in mind. Carry extra fuel. You might need to divert. Clean your airplane before you even take off. That's good advice. You might need to change your altitudes to get yourself out of those freezing temperatures or maybe out of a layer of cloud. Generally, icing, remember though, will be worse near the tops of the clouds, particularly cumuliform clouds. Earlier when we talked about, well, not a good idea always to climb. That's another good reason to think that climbs aren't always the best in small GA airplanes. Say you could get over top of them. but will you be able to stay over top of them later? I don't know. If you do encounter icing, let ATC know right away and tell them that you are in icing conditions and that you need to get out. If it's really bad, you might need to declare an emergency, but typically if you tell the controllers that you are in icing conditions and you need to change your altitude or your direction, they'll give it to you pretty quick. All right, if you cannot climb or descend, turn back, go home. Keep your bank angle shallow, and then let other pilots know and file a PIREP. All right, so we're getting very close to the end here. This last little bit is mostly for ATPL, CPL people again, tail stalls. When it comes to tail stalls, you need to remember that your horizontal stabilizer collects ice much quicker than does the main wing. Now, what happens with this is that, well, you end up with a stall potentially that really isn't like the normal aerodynamic stall from your wing. So typically, here's what's happening. Remember, the horizontal stabilizer generates lift downwards, right? So if your horizontal stabilizer collects a lot of ice to the point that it actually stalls prior to your wing stalling, you are actually going to end up with a sudden and violent pitch down. Now there will be some indicators that your tail is getting close to stalling. Typically what will happen is the elevator will start to flutter a little bit. And that's because of the high angle of attack and the flow separation on the bottom of the horizontal stabilizer. So you'll feel in your control column possibly a little bit of a buzzing motion back and forward. Unlike with your wing, where you suddenly feel the buffeting in the core of the airplane. Now, here's where it's really, really, really weird. When it comes to the recovery, you actually do what seems to be the opposite of a wing stall. So, right here, you can see the recovery procedure. Recognition, first of all, as I said, control column, some, well, oscillating. When you stall, recover by actually pulling back. Whoa, blow your mind, right? That's because, remember this here, by going upwards, it's at a very high angle of attack, I need to pull it back as much as I can and reduce the angle of attack on the stabilizer, not the wing. The stabilizer has a reversed angle of attack. Another thing I should do, raise the flaps. That again, if I put my flaps down, that's going to cause the air to flow over and to come down at a steep angle. Again, a high angle of attack on my stabilizer. So put those flaps up, now I'm going to reduce the angle of attack at which the airflow is meeting my horizontal stabilizer. Now, the final thing here, reduce the power, all right? Reduce the power instead of increase the power. And finally, we really don't want to pitch forward at all, so do not try to gain airspeed. If you try to gain airspeed by pitching forward, you're going to increase the angle of attack on your tail again. That's not going to work. All right. So those are more advanced techniques, as I mentioned, more for the ATPL to know and the commercial pilot to know. All right. If you suspect that you have icing on the horizontal stabilizer, approach on the proper speed for your configuration. Maybe don't put those flaps down, because when you put those flaps down, the angle of attack suddenly changes, and that can induce the stall. Use small bank angles and definitely avoid pitching down. And thrust changes, keep them at a minimum. The final thing in icing to talk about, this does apply to everyone, so hopefully the rec pilots and PPL pilots are still here. Hoarfrost. Now, most people think of this as forming on a nice winter's day, and it typically does. However, what you need to be aware of for the written exam and in practical flying is that if you've been at a cold temperature, kind of like we showed with cold-soaked fuel, it is possible for you to descend into a layer of warm, moist air And then what will happen is hoarfrost could form on your wings, even though you are in clear air. I know most of this presentation we've said, avoid clouds, avoid temperatures below freezing. Well, this is one of the only cases where you can pick up ice in clear air. Cold airplane moving into a warm, moist environment. How long will that hoarfrost stay stuck on your plane? Well, about as long as it takes for your airplane to warm up to the existing new temperatures. All right, I know that last slide we said this is the last slide, and finally is what we said. But breaking news from the exams here, and we just gotta go over this. So one topic that pops up now is something known as aerodynamic heating. When it comes to aerodynamic heating, remember that this is the rise in temperature of the aircraft's skin resulting from the compression and friction as the aircraft moves through the air. So it's a little bit like rubbing your hands together really, really fast, right? Your hands heat up. The skin of our aircraft will do the same thing, and this can help offset ice formation. The thing, though, to notice with aerodynamic heating is we got to be going pretty fast for it to prevent icing. An airspeed of 500 to 600 knots is required to ensure that no ice will collect. And you can see here that we've got from the Air Command Weather Manual, we actually have diagrams showing the temperature and how a dry airfoil at certain speeds heats up. And notice that if we have a wet airfoil, that of course it's not going to heat up quite as quickly or as much. Now, here's another important thing to remember. Sometimes people might think, well, if I start going at 500 to 600 knots, I'll have enough of a temperature that I'll start to be able to melt the ice that's already accreted on my wing surface. Well, that's not the case. Once ice is formed, aerodynamic heating is very ineffective in removing it. Okay, there we go. So now I think that's completed. We started out, talking about freezing to please, and all of this talk about ice has got me feeling really, really kind of chilled, to say the least. I'm suddenly thinking about warmer locations, like, something tropical, Fiji, maybe Mexico, not quite tropical, but still very warm. All right, till next time, I'm going to go thaw out. I'm Aaron, the pilottraining.ca. Now, I know I said it was cold and that I wanted to end this presentation, but hopefully you've been watching this over here, because this actually is from, you can see NASA here, and they're actually showing a time